Yeah, go ahead.
Okay, so we just get started. So today I'm gonna present this paper is called Biological Network Integration Using Convolutions, which is published in Nature Methods. So before I was going to detail about this paper, I want to talk about what is biological network. So basically, as you can see from this picture, so biological network is basically just a graph, a representation of how the biology components interact with each other. So in this one, we can see how the protein communicate to the metabolism and how the protein interact with another protein by using the gene regulations. So in our case, all this node will be the genes, and we have the different gene interconnections to represent different biological functions. So why it's difficult to doing the biological network integrations? So basically, what our target here is actually to integrate every network together to formulate this large size biological network, represent not just one, like represent a lot of like biological processing here. So the input for our initial networks will be like this small networks. So each one maybe represent just one functions, and we just try to integrate all of them together to formulate this one. So how can we like incorporate all this information together to formulate this one biological networks is this paper's target. So they proposed using a convolution network, graph convolution network layers to like integrate all the node information together to formulate a new feature matrix and integrate everything together. So here is a review of the.
Here you should learn how to draw this over chart, overview chart. So it's very nice to do.
Okay, here is the very basic method overview. Basically, we have multiple networks converted into adjacent matrix, and that would be our input for the graph convolution networks. And after the convolution networks, we will get the updated feature matrix for each one of the networks, and we sum up all the networks together to get this integrated feature matrix.
Is that summation or just a concatenation?
Summation. I will go into detail about every steps later. So this is the integrated feature matrix for all the input networks. Once we get this, we have like two sub steps to do our model. So the first one will be our autoencoder, basically just trying to minimize the integrated network weight compared with initial networks, trying to minimize the loss here. And another one, if part of our data has some labels like gene functions labels, we will predict the labels and find the minimum between the true labels and our predict labels. So combine all them together will be our loss function for this model.
Basically, part of them are unsupervised. Reconstruction, part of them are supervised.
Yes. And if we don't have any like labels data, they will be just like a autoencoder. It's totally supervised.
So basically steps 3B and 4B
we don't have that. Yes.
Okay.
And do you have a question?
So you iterated, that's how we get the network design, right? The nodes and the
not really
weights.
Iterated. So iteration part will be only in here.
Okay.
So we will get like the representative feature matrix for each of the input networks. So that's only happening here. We just sum it together. We get this one matrix for all the input networks.
So it goes from 3A to 4A and then it goes back again?
No, it does not go back, that's just the law.
Okay, got you. Okay.
So the structure is really straightforward here. Like it's nothing fancy here at all.
Okay.
Yeah.
So what is the reconstructing all the modalities network?
I will just go to input details. That's just the overview of the
Yeah, I mean, you mentioned reconstruction. So what is it reconstructing?
The initial input network. Yeah. So so I was checking of their input data. So they were actually using the three input networks, and this is the like the screenshot of the edge list to represent show the.
But that was 3, only 2, right?
No, that's just like they using different data types. So they have 3 data sets They have 3 data sets, and each of the data set have like gene networks. all three gene networks, and another one have like protein networks.
I see.
Yeah.
You mean from different databases, but
Yes.
each of them composed of two type of ages. One gene. correct?
No, actually they have three types of data, and all this like three types of data, each one of the test data have three networks. And these three networks belong to one type of like data, like genes only,
Oh.
or it's proteins only. I didn't see they actually have the networks from gene and protein and then combine them together. No, I didn't see that.
So they only have gene networks and protein networks. And
Yeah,
separately.
two different tests.
I see. So that's why they have multiple graph inputs, right?
Yes, they all represent the same thing. So if that's the gene input, which means the node will be the gene, protein that will be the protein.
Okay.
Yeah, so I only check the gene part. I think that's enough. Here is the input data, basically the actually listed to represent the graph data set. And we want to check how they do each of the steps. So
Okay, I have a question, actually.
yeah,
Yeah, and the input is two kind of difference graph for
that's
one
true.
for gene, one for protein.
No, they all have the same type of
Okay,
networks. Just the network construction is different.
I
They have different connections, but they all represent genes, or they all represent proteins.
like two different graphs represents two different gene
Gene
connections.
Right.
And then when you do the when you do the GCN, do the autoencoders and reconstruct the graph and then calculate the reconstruction loss between the reconstructed and two
Input,
inputs together.
right.
I see.
It's like very much like what many other protein group. But you got that you say just treat it as a different modality, right? You get a value for each, and then you get a joint Z, and then you reconstruct from that. You got the like right. You from that CZ, you have different decoders. You got the original reconstruct for that.
But there's only one decoder, right?
There's only one, yes.
But if that's only one decoder,
It could have some bias, right?
Right.
If the two inputs are quite different, then
Yeah, maybe I should go into details before I
Okay,
actually
okay.
how to discuss the performance of the
but must
model.
have very different decoders. If that's only one decoder, then the Z is the same. There's no way you can get two different graphs.
Okay, I will just go into details. So before we go to like more detail about this, I want to like see how is a graph convolution network works. So right now for the input data, we have like a feature matrix and adjacent matrix. For the adjacent matrix right here, we need to add sub loops to incorporate the feature information into our matrix. And for the feature matrix, we actually using one hot encoding to represent the feature matrix. So actually for the gene interconnections networks, the only one feature for one node, because that's just the gene expression level. By using the one hot encoding, the size of the feature matrix will be the same.
So the one hot encoding is used to represent the node, right?
Yes,
The node embedding.
right. And so that's just a very standard graph
It's
convolution.
not you
network.
mentioned this better with it. So
Yeah, I mentioned we should have embedding for genes. But this is somehow different from what I said. So my idea was we treat each gene as a word. We have embedding for each different genes. So if we have 20,000 genes, we'll have 20,000 different kinds of embeddings. But here, since it's one hot embedding, and according to the graph, for example, we classify genes into 5 types. Is that what they are doing? We will only have 5 different embeddings for each node. Is that the case?
No, I don't.
Then
but they still represent the gene as a, so basically that's still gene embedding. There's
But-
node in the graph with gene.
yeah,
I think
and
they have a different strategy to like to reduce the dimension of feature matrix. It's a little bit different.
I mean, if you say one hot encoding, that means you can only have a certain number of different types, right? If
No,
the
not
gene-
necessarily.
No.
Not necessary. They're the one here file, like that's just the illustration.
Yeah,
In
that's
reality,
exactly-
the vector could be huge, could be thousand.
Yeah, but okay, it could be 1,000, but I guess it won't be too much. You cannot have can have the same number as gene. Right,
So
it will not be the same size as gene. You can have a 20,000 dimensional vector.
Actually, that's how they did it.
Okay, so they have the.
20,000, yes.
Okay, so all,
Large size of feature matrix, we find another way to reduce the dimension of the feature matrix and then put it into the neural networks. I will talk about it later. Yeah,
so basically they really use the very
like large sparse.
to represent. So basically that I think that's not a very good way to represent the node value. Yeah, but anyway, that's how they did it.
oh, we'll see how they reduce the dimension.
Okay, and that's how they construct the input data. And then for the like very standard graph convolution networks, we just find this, which is using the training the weight and doing the dot product and then apply the nonlinear RT activation layers, and then we find the representative learned feature matrix.
Okay, I don't understand this, right? Like, no, it seems like confused.
Wait, understand which
So-
part?
So
The formula.
For this
From-
right here, that's like a very standard.
how they did it? If you look at this, can you understand how they do graph convolution?
I can try my best to explain it. So before, so if we don't do like, if we don't add some loops right here, so if we just dot product these two matrices together and each of the output will be like sum up all the neighborhood together, right? And if we add in the self loops, we will actually including the feature itself, so feature node itself into our like feature matrix together. That's why we adding these self loops. Otherwise, we will just have like a very standard adjacent matrix. And actually, it's a start because it's actually standardized adjacent matrix. We cannot use it directly because it will introduce some bias, I think. And after we doing the dot product, this is actually the weighted sum of the neighborhoods.
So
of this
W is
perspective.
the weights,
Right.
A is the standardized adjacency matrix.
Actually,
Can I
just
tell you
this-
which are the labels?
I think W is the weights from a linear layer after the matrix multiplication or before, right? That's for G, and then you have a linear layer and you also have this matrix multiplication. And I think W is from that linear layer, not from the matrix multiplication. The matrix multiplication you described is HA. H is the node features and A is the standardized adjacent matrix.
Mhm.
W is the weight for the
For the linear.
for Mark's question for the linear layer. W. I think so.
Yeah.
And you
So I
mentioned,
think that right here, this one is actually the trainable parameters.
yes, W is
W is
trainable
not-
parameter from the
I think
linear.
that's the linear layer, right?
Yeah.
I know, I actually find this function from another like some tutorial,
Yeah,
but I feel like that's just a thing,
yeah, the same.
right?
And you mentioned we have one hot encoding for the genes and they reduce the dimension. That's for H, right? H is for
Yes,
one hot encoding and then somehow reduce the dimension.
right.
Okay, we'll see later what it is. I'm very curious about this.
They didn't actually spend a lot of time, like 2 sentences to describe how they reduce the function. I don't think that's the main point of the paper, but we will see. Okay. And so this is like what, okay, any question about this one?
Only question about H.
It's not really about like the computer, but more like rock convolution in general. Is it rock convolution practice to introduce the self loop or is it?
It is common.
You should, yeah.
Yeah.
So this A star, I think it's a adjacency matrix, add self loop and then convert it to, what is that called?
So-
Laplace matrix.
If you don't exactly, that means you don't, when you estimate the cell, right, when you try to update the embedding for the node, you do not consider yourself. But in reality, right, yourself is the most informative information that you can leverage. So that's why you need to aid the self.
Okay, so in the paper, they don't actually using the very standard graph convolution networks. They're using the variational graph convolution layer is called a graph attention model. So what's the only difference is that before we actually summing up all the weighted together to represent this amount information. So in the attention models, they actually have the weight for the different nodes. So the importance for the neighboring node will be the difference. So as a compared to our function right here, instead of using A star directly, they actually have the weighting coefficient here. So we can see it's actually weighted adjustment matrix in our model. And so I don't think they do it right. It's not GC and it's GH. Actually, they're using 3 stacked DAT layers. So and instead of using the final output from the very last layers, they actually combine the intermediate data set after each of the layers, combine all of them together just by adding up the non-concurrent, just adding up them up together. So what they did right here is because the one layer will be representing the neighborhood of the given node, and another layer will giving us more like a higher neighborhood information. So these 3 layers will give us more comprehensive neighborhood information to here. That's why they have like in the beginning they have like this iterative N stacks. That's how they did it here. That's the only iteration information in this model.
It's like how much ages away you want to aggregate, right?
Yes.
So that's one order. That means I only care about the right names. And that 2 means okay, more, right? So
Expanded.
more.
Depends on the-
Expanded information.
So I think 3 is a bit.
Or- I think that's the after they did a hyperparameter training. They found
Do
this
they
one
put like last bit on the? Yeah, maybe
They
that's
just- they sum them up together to get this learning feature matrix. And H1 here will be one feature represented matrix for input node network 1. And after they get that, we can have like a different network will give us different H1. So that's one H1 and that's another H2, and they sum up this 2 network together. And they didn't not just directly using the element-wise summation. They actually using a method called like weighted stochastic masking summation method to combine this together. So how they actually did it? So before, one thing I forgot to mention is that the input network, they have the different node, right? Before they actually put into the graph convolution network, they're actually using the union node. So which means all the input network will have the same number of nodes and maybe different weight. So if you see network A doesn't have this network, but it doesn't have this node, but it does have that in the next one, they will still keep it, but for the 0 values over there. So that's all our input network will have the same dimension. And so since they have that, so we will have they have a they have a mask factor to do the summation. So if this node is present in the input node network, we will assign this value to 1, will give you the highest weight for this feature vector. If this is represented in the network and only unique in this one network, not in the others, we will assign to the highest weight to the feature matrix. But if it doesn't present in the original network, we will just assign to 0. And for all the other features, like the union nodes, we will assign to some like random numbers, like since it's something from binomial 0.5, just randomly assign to a value to there and then doing the weight. So all the summation of X will be 1.
Node is unique, it give 1 as a weight. It's not. It give 0, and everything else give a probability. Okay.
Yes.
Makes sense. And what is SG there?
SG. I forgot.
So what is otherwise? So otherwise means the node is in both network?
Yeah,
It's unique, but it's not unique.
Okay,
Yeah. Sorry, I forgot what the S1 is.
But that's SJ.
SJ.
So N is.
SJ is a it's a learnable
It's
convolution.
learnable.
That's why I didn't put it here.
So the N is the dimension of the vector. So the J must be a weight of something. So it's learnable, you mean it's learnable parameter, right?
SJ, yes.
So basically the weight for
Wait for
each of
each of the
yeah,
networks.
each dimension.
Yeah, so for the each network, now I guess it's not.
So,
Network will be different, that's why they have like this coefficient.
so that's why they call it stochastic, maybe because they sample that's from the balloon distribution. There.
Yes, so that's just like random.
Random.
Random dropout of the,
0, 1, 0
figures.
binary.
yes. And after the random dropout, they just like bring the scale at the same scale weight for that.
Why are they doing this? So basically randomly through masking out 50%. Oh, okay, if that's a very important one, they don't mask it, right?
Yes,
So that's
Only
that's
like
unique, right?
union, no, they must, the union.
If that's all okay, you do it, mask it out. Why are you doing this? Why doing this? What is
Random dropout.
Yeah.
I feel like that's the same thing when we do the deep learning model, when we using the dropout layers, will giving us like high performance. I feel like the difference the same thing, since they have so many nodes, maybe not every node.
So here is basically they want to combine these two, right? 1 and 2. So that's why they say n here is 2. So they want to combine these two, and then there's a strategy. Okay, if that's a node only 1, that means that they don't want to
remove that.
they want to
give
keep
it
this
high-
information.
Yes, high.
Right, and if that's a 0, if it means that both of them are all empty, they don't that it's empty, so it's 0. They set it as 0. So and then if that's okay, if that 2 means this node is not unique, both of them has a node,
Mhm.
right? If node is there, it's all unique. They want to keep it. If that's not at all, they will remove it. If that's in both, they will. Why is that? Suppose that's
So just give the highest weight to the unique node, and all the other union node will have the different weights.
still the why they want to do best the custom. Yeah, can anyone explain this? Why? What is benefit from this? It's just they want to combine these two vectors, right? H1 and H2, and then they want to do it in the weighting. So if you don't have the MI there, MG there, they just do weighting of that. So it's unneeded, understand. And the MJ there is actually for masking, right? And then okay, masking is certain rows of doing that. So right, they want to, if there's no unique, right? They don't want to mask it out. If that's the row is not, if that's node is not in or right, in extended, then they don't want to get it. But if in the middle, okay, if that's say if the both H has the same node. Anyway,
I don't think they actually explain why they want to add in the reports. They're in the papers. They just like overall see how this actually works, just mapping the notes to the. Yes.
So why did they do F times dot product F inverse?
Oh, I haven't.
Or not there yet?
No, not yet. We're still in the very first stage, but
go ahead. Basically, there's a way to combine it. Okay.
yeah.
In a stochastic way to combine.
Yeah,
Yeah.
so the output of this H combined will be the actually the how many neurons they define in the graph convolution network layers. So, but they don't want using that directly because it's so large, and they actually apply another linear layer here and reduce the feature matrix, the size of feature to 512, and then they actually after they doing the linear layers, they get this feature matrix F. And since it's only the representation of the node, they did the self dot product of the F times the F transpose, they get adjacent matrix. So why they did it here? Because they only have like a representation of the feature. They don't have the connection between the node. So that's how they get an adjacent matrix. So basically right here is like a representative of the overall networks, and it's converted to the visualization part. And after they did that, that's just the combined integrated network, biological networks, and then they trying to find the difference between this network that's over equal networks, that's over like integrated networks. So here is in there, loss function, they find the difference between this A prime and only input A1s, for examples, and then we did it with we did element dot product element multiplication of the two matrix with the binary mask. It's the same idea with this M mask. If the node is already present in the original network, we will assign to 1, and if it doesn't, we will make 0. And that's they doing the mean square error to like minimize the difference between the integrated network and the input. Any question here?
Maybe you explained it, but how do they know, like, so you have the main graph from the agency, and then how do they know to split it into those two? As opposed to another combination?
I think they didn't actually hear too much about how they actually connected, but they hear much like how they connect. Like how like what's the weight of this they connected. I don't think we really care about it. So they just find the difference for this. So that's why they have the binary mask. So if that's node is already in the original, like already in the original networks, we just minimize the difference between those two. But if it doesn't have in the, if it doesn't in the original networks, it will just leave it to 0. We don't care about this node difference.
Okay.
Right. Okay.
So I can see from the adjacency matrix, we generate one graph. How did they split this one graph into 2?
No, I don't think they actually did it. They just using that to calculate the loss function, but they didn't like mention if they want to go from the integrated network back to the original input
So they
network.
just
They didn't
compare-
actually doing that. They just
The
doing the,
input is two modality, the same that's modality.
yeah, that's just, I don't think they actually put it back. They're just using it to like calculate
So it
the
means-
loss.
I mean, so the loss is computed between one reconstructed network and 2 input.
With all the inputs, yes.
Okay.
Yeah, and then doing the mean square error for that. And that's just for one input network, they calculate the difference between this and that, and then for the rest of them, we'll do the same thing and do the mean square error to get the loss function for that. So that's basically
Oh, I
the,
see. So what they believe the green one is the true one, but you observe one are partial one.
yes,
So they calculate a lot to minimize the difference.
right,
So they find the one green one that's fit all observations you have.
right. So that's our target here in this model. We find
Yeah,
the
but then
integrated
they
classes.
try because the, because there's a, say, there's a missing or incompleteness. So that's why they have a random dropping there, a binary mask. Right, if you directly calculate, then there's no way you can model or account for this. Missing, right? So then if you have this kind of randomly masking, then you can somehow model that. Okay, yeah, basically random through some edges away and see, okay, whether in that case, you mimic the missing, right? And then you compare that.
Yeah, but I just like because actually that's a question from here from me. So since I just feel like that's just a adjustment matrix. That's how the gene related together, right? The edge. But how about the feature matrix? Because is it because this adjustment matrix actually come from the feature matrix? All the information is already included in the adjustment matrix. We don't care about the feature matrix here. That's why we don't have the loss for the feature.
Because your input is it is a graph.
Right.
Graph itself is already is a distance matrix,
Mhm.
right? They care about the graph, the relationship between them.
Okay.
So, but that you have to learn the value for each node, because with that you actually, I suppose you already have the value for the node, then you can directly infer the relationship between nodes, right? Basically, value you calculate the distance or whatever. So basically, this information is coupled.
Oh, it's already integrated into
Yeah.
this, right?
So if you have the value, you can infer that a prime estimated.
Okay,
Yeah.
yeah. Okay, that's how they do the auto encoder part, and as I said earlier, so the next step will be the semi-supervised one, as some of the gene have the gene function labels. So this one is really straightforward, so that's.
One more question. Did we get A by matrix multiplication between 2 nodes embedding?
Yeah, that's the how
Yes.
they did it, right?
Yeah,
You see,
So basically, A is just a tensor between these two.
sort of, yeah,
Okay.
sort of like, if you have like a imbalance for the node, right, you always calculate how similar or how different the nodes are. That represents, say, the Egyptian matrix, right?
And you mentioned this
Right.
will introduce a lot of false positive before.
Which, what possible?
Right here.
So you reviewed another paper a few months ago. You said if you use attention to calculate the edge, that might introduce a lot of false positive. Right. But anyway, that's the method. I kind of got it.
Yeah, but then they have control, right? You have to be similar to original input,
Okay.
right? It's not like you're totally just based,
Oh, all right. So they have supervision.
not supervision, it's like sort of for constraint, right? Because you have to be similar. So I guess this is the one over here. It's like the modeling, like the random dropping you have to see is a little bit more. And I never saw it. No, I saw it, but it's not like a common trick. It's people use.
Okay.
Yeah.
And for the supervised one, they're using this matrix again. Some of the features actually have the labels, so they put in the classifier.
It is just a value for.
So for the classifier, so before that, each node represents genes. After we like test this with the overweight layer, so we get the genes and its corresponding probability of the labels. And by minimize the two labels, difference between two labels and predict the labels, they get the supervised loss function.
That's just cross
So that's the
entropy.
cross entropy.
Yeah.
Yes, just cross entropy loss. And so for the overall for this model, here is a total loss. For models right here, so we have the lambda as a hyperparameter for a model. So if we don't have any like supervised data, it will be 0, right?
They don't even need that. They only need a lambda last one, like one lambda. You don't need a binding minus.
Yeah.
Yeah.
So that's basically overall with this model. That's it. Yeah.
What kind of labels are they assigned? Like,
They have like, I didn't like actually doing the checking their answers, but I feel like this maybe gene function labels.
Like pathways, categories, functions, yeah.
Like when we're doing the latent space representation of the single cell data, we have like the labels for each cell, right?
Yeah.
From the different
This is
types.
not cells, gene.
Yes, but I just like saying like similar.
okay.
The labels are from nodes, right?
But not for gene.
Each node is actually a gene, so I feel like the same thing.
Gene or protein, right? So I guess.
Or
what-
it can
Is
be
it
like a
a
protein or whatever.
From there, isn't it not for like each like network, if there's a label, or is it? Because the genes are the nodes, no?
The gene have labels.
Yeah.
Each
Okay.
individual node
Okay,
has
they-
actually corresponding a function corresponding to this node. So each node will have labels, not the connections.
The gene has a specific functions, right? So the function could be put into categories.
It's the columns that have labels.
Yes, so basically it's like the feature. I mean, I feel like this is a categorical thing, so multiple genes can be corresponding to the same labels, that's
okay,
why
okay,
they have
okay.
like this kind of categorical labels.
Okay,
Right.
got it.
That's how I understand that. I didn't actually looking at their data, but
It's in the level like a pathway, right? So one pathway, is in each pathway you have 100 of genes.
So we're trying to understand that graph. So it's each row is a gene, and each column is like an annotation which like label. Okay.
Okay.
yeah, and that's pretty label will be.
Yeah, you gotta say the cell type.
Yes, sometimes that's the word I'm looking for. Yes, sometimes. Yeah, so that's basically what our overall models looks like. Other than the method, the rest of the paper is talking about how they actually evaluating the performance of the model with other 2-3 biological network integration methods. So, but before that, I find some like interesting idea. Because this is what I'm talking about, the input data set.
So I want to have a very quick comment. So if you look at the methodology, their methodology is not complicated or more advanced than our methodology. But why they can publish in this method? First of all, they have novelties, because the problem is not. It's not novel anymore. But they do have methodology innovations, and then you can see the figures that's called are very nice looking. So I keep seeing that, I keep emphasizing that, it's really important. If you want to get those people admitted or accepted at the top journals, you have to impress the reviewers, the editors.
How do you make the good graphics?
I don't know, I was also learning, you know.
Oh, that takes forever. So slow.
So I know there are people using some, say, Illustrator, Adobe Illustrator, BioNic, a lot of tools to use to have.
Just to make these?
But this you can use in PowerPoint, but the problem is not what kind of tool you're using. It's how you're gonna put your ideas in paper on PowerPoint. Right? How you gonna organize this? How you gonna make the information flow smooth, right? So that's changing.
So this question, because I was always wondering, depending on where you publish, does it really depend on the novelty of your idea? It depends on how you present it. That's what
Suppose. So that'll tell you an equation. The methodology 70%, right? The topic maybe 20%. The remaining is just the figures and the writing, right? So I guess more the figures and writing will come for more than half.
Okay.
Of the points. But of course, you have to be right. So the topic also, in many cases, is yes or no. Right? Some editors they have preference on certain topics. Right? If you're not in that topic, they will think, oh, that's not interesting. So it's like a yes or no. Right? That's there's no way you can deal with it. So you really just try a few tutors, and then if you're lucky, some editors like your direction or your topic, right? Right? They will send it out for reviews. But in our field, right, we are doing single cell spatial, single cell drug discovery. I don't think we have to worry about this topic. That thing, there's a lot of professors doing very old stuff, right? Only secondary structure, those are old fashioned. They may have problems with that. So for us, we need to care about the novelty. Novelty is like, okay, in this field, we know this field is important, right? The editors know. Can your method solve a real challenge in this field, right? Do you have novel compared to existing method, right? So that's the part you should. It's the same for everyone. I keep speaking, right? Keep asking you, like, what is the novelty, major novelty of your method, right? So you need to somehow present that, make that information clear to the reviewers, the editors. And that's the second important thing. The last one is how you're gonna organize, right? Maybe the reviewers get the point, your method is good, right? The topic is good, it's very important. You have novelties, but you're really bad in presenting those. And you make people think, oh, you present, you claim, you make strong arguments, but you don't have sufficient evidence to back it up, right? Okay, you say, okay, you have so many novelties, but you barely shoot any of that because the bad presentation, right? Bad figures, bad result, bad discussions, and then you don't have sufficient evidence to back up your novelty argument, right? That will also kill your paper. So basically, you need a good topic, you need enough novelty, and then a good representation to back your argument of this novelty arguments. Yeah. So I guess, yeah.
Okay, so talking about input data set, since we are using, that's one of the data set they were using to doing the test. This data set have three input networks. One is the gene correlation networks, have this many genes and this connections, and another is a co-expression network from transcript profiles, still represented by genes and interactions, and the protein-protein interaction networks also represented by genes, gene and bacteria. So that's what I think. Even though they have three different networks, but each node represents they all represent genes. So since they are,
I guess the method is not scalable because you see they're using yeast level, not use human or mouse.
they have that.
Oh, they have it?
Yes, they have three different types
Oh,
of
so-
data.
So I just take people with humans, yeah. Three people.
Okay, since they were using the one-hot encoding, so the feature matrices stats will be like the or two of this the number of genes. So we have like this many of the factors is around like 20 million. That's my calculation. So it's around 20 million size. So which means the input neuron for graph convolution network will be the 20 millions. And including this two networks, total will have like around 23 millions neurons in our data set. In that case, we cannot fit our model into GPU. I tried it before. Yeah, you cannot do that. And for the adjacent matrix, this very sparse, so they using sparse matrix when you do the dot product. So this adjacent matrix didn't really actually impact the GPU burden of this. But still, that's the trainable data is still like taking them to this spaces. So they actually using another method called singular value decomposition method to get the normalized lambda max matrix of the union networks. So right here, they're actually using the union graph to contain all the nodes, and the edge will be the maximum edge of overlap edge to have like one combined union graph. And then they using the singular value decomposition method to reduce the feature size of the union graph, and then using this graph as the input for each node networks.
Yeah, I can ask one more how they did it, how they managed to train the model. So how they're so rich. I don't believe they are like.
Well, I actually mentioned their like GPU, not GPU, they actually mentioned their CPU is like a 13 gigabytes. So like this like 12 gigabytes of RAM.
Yeah, it's not powerful than ours, right? Why?
Yeah.
How they manage to train it?
I mean, they can reduce their size to whatever like number of features they want. After they like reduce the size.
So they're not directly trained on the 20 million.
No.
SCD is for dimensionality reduction.
Yeah, and then they reduce the dimension and then training that instead of using training the original feature matrix. That's how they did it. But
So that this is not an optional step. This must be or like must have step, right?
yes. And for the model training, I find that their original like the log file, they find they have like very large epoch numbers, like 2000. Is that normal in like network?
Yeah. That's another. Given the size of that, I'm not surprised.
But my model only use like
It depends on when you can convert. There's no
okay,
like
there's no,
yeah.
for that. Okay, I guess those that have so like large equal numbers will have like more longer training time. Yeah, I think
Your model is also huge, right?
I mean mine is like 0.6 billion digits, so that's even like higher than this one. So like 600 million digits for mine. And that's just the model evaluation. So I want to like very briefly go over this, like just one of the evaluations. So I don't know anything about the biology networks. I don't know how to like evaluate this kind of models. So I just want to check how they evaluate their models. So basically they try to find the gene correlate co-annotation predicting this predict the gene by gene pair relationship. So by using the precision. So if they have find a gene like true positive or false positive, something like that, then the gene by gene prediction, that's one way to evaluate the model. Another one is the like gene module prediction detection. So what is the gene module is actually the gene, like all this like cluster gene together represent some like specific function, biological functions. So my understanding here for the gene module is actually gene cluster. So that's why they're using the AMI score to like to check the clusters difference between the actual one and their predicted one. And the last one is just easy the gene function prediction, how much percentage they predicted, right? The accuracy of the gene. So that's overall that's the data.
If you look at this method they compare, they're all like embedded learning, like node to web, which is embedded learning for the node. So basically, it just get a value for the genes, and then based on the value, they can cluster the genes, and then they can compare with no gene groups. Yeah. So basically, yeah, that's some degree of statistical results of knowing the value for the genes.
Okay, that's it for the papers. Oh, for my research, I didn't like progress a lot since last time because I'm present very last at the end of semester. So like this is the view of my like project.
Did you want to speed it up from now on, or?
That's I'm still working on it. So, that's it. I think we can figure out this for the rest. That's it for my.
Try your best to progress faster. Otherwise, I won't let you go home this summer.
Oh, any questions for this?
That is very good paper.
Okay, then.
Yes,
that's it.
right? I know one more is very good. Probably the best.
Wait, if you just both go to China at the same time, could you research there? Oh, wow.
No.
That's a good proposal, I'll say.
Oh my god.
Yeah, we try again, so. If you like. We can, I guess most of us will go back to China, or except you, you too. We can have a group meeting. in China. Still.
I have a question about node features. Node embedding. They first have a one hot encoding matrix for each node. And then before they do the dimensionality reduction, what did they do? Or they directly applied the SVD to the one hot encoding.
Yes. They didn't do any like machine learning stuff.
Wait, so
that.
this, I find it a bit weird because SVD is something like PCA.
Yes.
And one hot encoding doesn't contain any information. It's just saying I assign a number to each node, and the order of the node decide how that feature map looks like. So if I change the order of the node, then the result of SVD will be changed. But order of the node doesn't have.
So even here, they use somehow the graph convolution, right? So even though there's one hole, right? After this graph convolution won't be one hole. It contains information on a similarity.
I mean, SVD, I think that's done before the graph convolution.
No, it should be done after that, I think. Is it?
I think it's before.
Before that, so they use
Otherwise, it
SVD
will have like very large.
to get the embedding. Then after they get embedding, they use the embedding in graph convolution. Then think about it, if you change the order of the gene, the embedding will be changed. Does that make sense? I feel that's too complicated. Just assign an embedding to each gene, just like NLP.
So basically, they get one more encoding for each gene and then do PCA, something like that.
Yeah. According to that slide, right?
Is it doing that?
Yes,
Yeah,
I'm
it's
pretty
just
sure
like
that's
programmatic.
right here.
Why not just give an embedding, like 10-dimensional word embedding to each gene, just like NLP?
Anyway, yeah. So they do convolution, okay, you're saying that they cannot do it because of the size. So they have to reduce dimension first.
Then why bother having one hot encoding in the beginning? They didn't need to have that large dimension. Just to use the 10-dimensional word embedding, that's enough. And for each gene, this like other people's doing it. I heard some people doing gene embedding and then use that for VAE, and the clustering performance was very good. Just use that easy method is enough. Right. Do you see what I mean? For each gene, just treat it as a word. Assign it an embedding, and the embedding weight is trainable. We have a vector for each word or gene. That's enough. 10-dimensional embedding, and then use it for all the subsequent layers.
Like a VAE.
Yeah, for the graph convolutional, right? For graph convolutional layer, you need to have an embedding for each node. Then for the node, you don't need to use the SVD to generate the embedding. Just to do what natural language processing is doing. Just to generate the embedding.
But based on that, you see the right dimension only reduce at the end last step. Right, see there's 4, right? That's 5, right? And then the end is 2, right? So you're saying, oh, in the beginning, here why they should not that? Showing you, okay, the dimension only reduced in the last step.
I think these matrices are adjacent, these are for edges. I think they didn't show the node.
No, here, those are embedded.
Oh, no, for the node feature.
Yeah, you see here, now you have 5, but here is 2. It means the dimension reduction is here. Reducing is here, right?
No,
No?
I think that's just represented, this
Oh.
part. This part. But before that, they didn't actually show in this part.
What's the dot product, no? Isn't that how you get it?
I think that's just for the,
This is all dot.
for this layers here. And this is what they got after the graph convolution. But before that, I think they actually using a dimension reduction.
They show node features on the right hand side. So I guess according to this plot, they didn't do the dimensionality reduction until
Until
there.
like here.
Yeah, because you can choose, you can control the dimension of W so that you can choose how much you want to reduce. But anyway, I don't know. Or I can ask one more to see how to get in. All right. Yeah, go ahead.
And
Or we can, yeah, I think it will automatically save.